Hi, everybody. Hi. So, I'm sorry I'm a couple minutes late. I'm going to change rooms in about 5 minutes. My toddler's homesick today and he's sleeping right upstairs, and my wife is using our other room. So I'm going to, um, on a Zoom call, so as soon as she finishes, I'm going to go back to our usual spot um, to move farther away from his bedroom. Any questions before we get started? Can everyone hear me okay? Just want to make sure. Good. All right. Um, so where were we? So we've built the Lebesgue measure and proved various properties about it, tried to give various different characterizations and get a feel for it. The next step towards integration theory is to build the set of class of functions which we're going to integrate. So these are called the measurable functions. So let me share my screen, sorry. Something. Okay. All right, is my screen visible? Okay, great. So the measurable functions. Um, okay, and just like we built measure up from the beginning, we're going to build measurable functions up from simple functions. So this will become a technical term in a bit, but let's start off. So step 0 is the following function. So given a set E, an RD, we'll define chi E of x to be the function, which is equal to 1 if x is in E, and 0 if x is not in E. So this is called the characteristic function of the set E. Right, so it's a very simple function. It's just 1 if you're in the set and 0 otherwise. So it's a picture of one, just as a function from R to R. Here's the graph of a characteristic function. If E is an interval, the characteristic function on E is just equal to 1 on E, and then 0 outside of E. But note that I haven't specified what subset what E is. E is not necessarily an interval or a cube or a block. It's just any subset of RD for the moment, or just for any subset of RD, you can define a characteristic function like this. Next example, one is called a step function. And these, this is what we used to build the Riemann integral. So these are given by a function f of x is equal to the sum from j equals 1 to n for some number n, aj times the characteristic function of what I've used to mean disease rj of x, where rj is equal to a rectangle. And aj and r or c are constants. So it's just a superposition of characteristic functions on rectangles that are given different weights. So for example, if I have three rectangles, R1, R2, R3, say three intervals. Then a step function might look like this, say, oops. Where this is A1, A2, and A3. And then the function is 0 everywhere else. So these are step functions, and when we use the word step function, we'll be specific that these characteristic functions are only the sets over which we have this characteristic function are only rectangles. And the second example is slightly more general. What are called simple functions. And for these, we'll just relax the requirement that the sets be rectangles. So f of x, well, functions of the form f of x is equal to sum from j equals 1 to n, aj chi ej of x, where the ej's is a measurable subset of RD. The measurable subsets of RD. So given a collection of measurable sets, you can find a simple function by just simple functions are defined as follows, rather. And again, the AJs are real or complex numbers, depending on whether you want your function to be real valued or complex valued. Okay, and so these are some examples to keep in mind. The definition that we'll work with and try to start understanding is that of a measurable function. So we'll say f is measurable, f function from RD to the extended reals, say, is measurable. If for every A in R, the set F inverse, so the inverse, the preimage rather, of the interval minus infinity to A is measurable. So this is what this notation means. So note, or just to remind you, the preimage of a set is defined to be all x in RD. It's a subset of the domain such that f of x is less than A. So this is what the preimage of this interval is. We'll often use some shorthand notation for this. We'll define this as, we'll just simply write the set F, where F is less than A. So it's a set of all vectors in RD, so that f of x is strictly less than A, where A is just some given real number. And we need all of these sets to be all of these preimages to be measurable. This is a definition of a measurable function, and we'll flesh this out a bit. So equivalent definitions. A couple immediate ones. Well, one observation is that picking a strict less than there is somewhat arbitrary, or just maybe classical, but not important. So we look at preimages of these half-open intervals like this, but one could equivalently say a function's measurable if and only if f less than or equal to a is measurable. If and only if f bigger than or equal to a is measurable. The set for which of x for which f is bigger than or equal to a is measurable. If and only if the set when f is strictly bigger than a is measurable. So we could have equivalently taken either of these three characterizations as yielding the definition of a measurable function, and it's given what we've proved about measure. It's not so hard to see that these are equivalent. For example, if you think about what the complement of this set is, it's nothing other than this set, right? The set of x for which f of x is strictly less than a. Complement is just the set of x for which f of x is bigger than or equal to a, right? And so remember, a set's measurable if and only if its complement is measurable. So therefore, this formulation is equivalent to this formulation of measurability. But then, this formulation. And then, and then you can argue similarly to obtain these other two, other two equivalent definitions as well. Okay. All right. So that's those are equivalent formulations of measurable function. One other quick definition. We'll say f is a function f from Rd to R union. This is what I mean by a closed interval minus infinity to infinity. Is finite valued if it's finite valued. So if f of x is strictly bigger is finite for each x in Rd. And if we allow for this definition as well, if f is finite valued, then f is another equivalent definition for finite valued functions, measurable if and only if the set is measurable. For every a, b, and r. So that if just look at all preimages of bounded open intervals. If those are all measurable, then f is measurable, and vice versa. Okay. So this is the definition of a measurable function. And let's keep unwinding it to get a sense of which functions are measurable. So property one of measurable functions, if f is finite valued, or maybe let me write this, suppose f is finite valued. So just another characterization, it's slightly less immediate than the one's finite valued. Then f is measurable if and only if the preimage of every open set is measurable. For every open theta and Rd. And equivalently, if and only if the preimage of every closed set is measurable. Okay. And if f is not finite valued, so if it possibly takes the values plus or minus infinity, if f takes values and possibly infinite values, it's measurable if in addition the preimage of each of these 2 points is measurable. Okay, so if and only if every open set is measurable, and if we have to look at 2 additional sets, namely two additional preimages, namely the preimage of plus or minus infinity. And this property is again almost immediate from the definition, and given what we know about open sets on the line, right? Okay, so what this means is equivalently, so property 2, continuous functions are measurable. So f implies f is measurable. So the continuous functions are measurable functions. So we're not creating some crazy new class of functions that doesn't include the continuous functions. So the continuous functions are measurable functions, right? Because for a continuous function, the preimage of every open set is open, right? That's a definition. It's like one definition of a continuous function. And so since every open set is measurable, the preimage of every open set is measurable, is open and hence measurable. So continuous functions are measurable. If in addition f is finite valued, if f is measurable and finite valued, and say phi is continuous, sorry, phi is a function of real numbers, then phi composed with f is measurable. And again, this, so how to see this, phi continuous, I'll just write the proof in parentheses real quick. If phi is continuous, this implies that is equal to an open set, which implies that phi composed with f, the preimage of this function of is just given by the preimage of O, which is measurable. So that's the proof of property 2. So it's not true. It's not true in general. The more general version of this isn't true. So so warning. It's not true that in general, sorry. it's not true in general that f composed with g is measurable if f is measurable and g continuous. Right, we needed this outside function to be continuous here. So phi needs to be continuous. Okay, property 3 is if you have that measurability is preserved under undertaking sequences. So if fn is a sequence of measurable functions, then the sup, the inf of the fn's, the lim sup, and the lim inf are all measurable. So if you have a sequence of functions, you can define a new function by just taking the pointwise sup. So I'm looking at each of the fn x's, taking the sup over all n of those numbers and defining a new function like that. That yields a measurable function. Similarly, you could take pick any x, look at all the fn x's as a sequence, and take the lim sup of that sequence, which always exists, right? If we allow it to take values in the extended reals. This yields another function in the extended reals, and that's measurable if all the fn's are measurable. So so measurability is nicely preserved under these operations. So we're getting quite a general class of functions here. And note that the continuity is certainly not preserved under operations like this, right? So measurability is a weaker condition, much weaker condition than continuity. So the proof is just some set theoretic manipulations. So the set if I look at this function sup of fn, sup over n, fn of fn, set of all x for which sup fn of x is bigger than a. This is just equal to the union over n of the sets where fn is bigger than a. And now, since measurable sets are closed under taking countable union, we just have a countable union of measurable sets here, which is also measurable. This is equal to a countable union of measurable sets. Okay. And so that handles this sup. The inf is the same argument. Or a nearly identical argument. The lim sup for this, it's helpful to write this as the inf. We're just going to use the sup and inf characterizations of lim sup and lim inf in the first part of the theorem to prove this latter part. So the lim sup of fn is, remember, is the inf of all sups for k bigger than or equal to n of fk of x. Sorry, got my indexes wrong. There we go. So then this is just, this is a, this is a measurable function by the first part. and then again, we could take inf of a sequence of measurable functions. Okay, if you guys don't mind, I'm going to switch rooms. Just give me 1 second. The last thing I want to do is wake up a sleeping toddler. A sick sleeping toddler. Okay. All right, so where were we? Okay, so this is the lim soup. This is again measurable by the first part and lim inf. This is the soup of the imps, right? The soup. Okay. And so the measurability follows from the by the measurability of these types of functions. Okay, so that's that. And a corollary is that we've proved something quite strong, right? So in particular, if not only if so if a sequence is convergent, if a sequence of functions is convergent, just means the lim sup and lim inf are equal to each other. But by this previous theorem, these are measurable functions. So the corollary is if you have a sequence of measurable functions are all measurable, and they converge pointwise, is equal to some function f of x, then f is also measurable. So measurability is preserved under limits. And this is immediate from the previous theorem because we know that the lim sup of sequence is measurable, the lim inf of sequence is measurable. In this case, it just so happens that the lim sup and lim inf are equal to each other. So this is property. Maybe I'll call this property 5. No, property 4. Sorry, I think I lost count. Okay, property 5 is that if f and g, other operations we can do on functions are taking powers of a function or adding functions together. So the algebra with functions, namely, is preserved. So fg measurable. Then I f to the k for k bigger than equal to 1 is measurable functions, all measurable functions. And 2, f plus g are measurable. F times g are measurable. If both are finite valued. Okay. The proof of this one is a slightly trickier. If k is odd, this set where f to the k is bigger than a is just equal to the set when f is bigger than or equal to a to the 1 over k. Right, for any real number a, we know how to take kth root. If k is even, and a bigger than 0, then the set where fk is bigger than a is equal to the set where f is bigger than a to the 1 over k, union the set where f is less than negative a to the 1 over k. It was a union of two measurable sets, so it's measurable. And 2, this is 1, 2, the set where f plus g is bigger than a, this is equal to, this is slightly trickier. So I can write this as the union over R and Q of the set where f is bigger than a minus r intersect the set when g is bigger than r. So it's just a way of decomposing the set of all x for which if f and f plus g is for which f plus g is bigger than a, f of x plus g of x is bigger than a. And the point is now I've just characterized this set in terms of sets which I know to be measurable. And in particular, I take a countable union here. Okay, so you can think about that one. And f plus g, the key step in understanding f times g is the following trick. I'm going to write this as 1/4 times f plus g squared minus f minus g squared. And now I can apply the previous step along with the step about taking powers of the functions. So once I have this characterization, now I can rewrite the union. I can just combine all these previous arguments to prove that f times g is measurable. So measurability is closed under algebraic operations on functions. So this is a nice set. In particular, now it looks like a large class of functions, right? Once you have a sequence of measurable functions, you can do these crazy operations. You can take limp soup of that sequence, or just take soup of those sequences, and you preserve measurability. So this is a big class of functions. It's time now, I guess, to introduce a word we'll be using a lot, definition. So given two functions, we'll say that f of x equals g of x almost everywhere. So this will now become a technical word. Almost everywhere will become a technical word. We'll write the shorthand f equals g a period e period for a period e period for almost everywhere, if the set in which they differ has measure 0. If the measure of the set of x and Rd such that f of x is not equal to g of x, if this set is measurable. So in general, almost everywhere we'll refer to except on a set of measure 0. So we'll use this word for several different things, and we'll always just mean something happens except on a set of measure 0. So in general, set of measure 0. Okay, and then the property of measurable functions, property 6, is that once we know a function almost everywhere is measurable, then that function is measurable. So if f is measurable and f equals g almost everywhere, then g is measurable. And the proof, the two sets of x where f of x is less than a, and the set of x such that where g of x is less than a, can differ at most on a set of measure 0. Differ on a set of measure 0. Right, so you can write one set as the other set union a set of measure 0, and sets of measure 0 are measurable. Okay, and everything we proved before, if we just tack on the words almost everywhere, it still holds. So all properties, note, all properties from before can be relaxed to almost everywhere. For example, the limit if this limit holds almost everywhere, then this implies that f is measurable. If fn's are measurable. And tend to a function f of x at almost every x, pointwise, but at almost every x, then f is measurable. So, so these are the measurable functions. And so how to think about them? Well, a very helpful way of thinking about the measurable functions is just to think of them as limits of simple functions. So in particular, we can approximate every measurable function by an increasing sequence of simple functions. And let me formulate this as a theorem. Approximation by simple functions. Before I formulate this, maybe I should stop and ask if any questions have come up. No questions.
Can I ask one thing?
Yeah.
When we formulate simple functions, do we require the sets to be disjoint?
No requirement of being disjoint. I don't think so. Right, if the sets aren't disjoint, then you just add then the value that the function takes in that set is just like you just get counted twice, right? Let me check your book though. Let me make sure that I'm not getting myself into some trouble. Quite possible. Yeah, but maybe I should say I should include one more restriction. So a simple function, these are measurable sets. I should require them to each have finite measure. So each EJ is a measurable subset of R, and let me add on each with finite measure. So I like to think of my simple function as being built on blocks of functions with finite measure. I'm seeing some people in the chat. Whiteboard frozen for me. Is whiteboard frozen for everybody? Let's see.
Yep, at my side.
Oh, maybe because I changed. Okay, hold on a second. How about now? Did something appear now on your screens? Yeah.
Yep.
Okay, cool. Yeah, right. These might not be disjoint, but then I just double count, right? Is that okay?
Yep, yep, yep.
Okay. So, and if I give you one simple function where the sets are overlapping, you can write down an equivalent simple function by just taking the by just picking more, chopping it up into more into disjoint sets, kind of. Okay, so the point is that um, measurable functions can can be viewed as kind of limits of simple functions. So so the first version of this, let's assume that f is non-negative. F of x is bigger or equal to 0 for every x. If is a suppose f is a non-negative measurable function. Then not only can we approximate by simple functions, but we can approximate by an increasing sequence of simple functions from below. Then there exists a sequence of non-negative simple functions. I'll call them phi k, such that 1 phi k converge pointwise to f. And 2, I don't know why I'm phrasing it like this. Let me write this more cleanly, such that two things hold. Phi k of x, they're increasing, and phi k of x tends to f of x for every x as k goes to infinity. Let me refresh this. Back up the drop-off folder. So every measurable measurable function can be approximated. Non-negative measurable function can be approximated below by a sequence of increasing sequence of simple functions, and the proof is not so hard actually. We're just going to chop up So let's first we're going to truncate f. So truncation. For every n bigger than or equal to 1, like qn, capital N equals cube of side length n, centered at x equals 0. So just take the cube of side length n, centered at x equals 0, and set capital F n of x to be equal to f of x if x is in Qn, and f. So if x is in Qn and f of x is, sorry, let me be a little bit neater here. God, I hate writing on these iPads. F of x if x is in Qn and f of x is less than or equal to n. Equal to n if x is in Qn and f of x is bigger than n. Say bigger than or equal to n. 0 if otherwise. So we're just going to make f0 outside of the cube Qn, and I'm going to also not let it be bigger than n. I'll just cap it off at n. So I'm kind of boxing in f. And then note that as n goes to infinity, that the capital Fn's converge to f of x, right? Just taking n large. The box becomes larger and my allowable range for the height of f becomes larger and larger until I capture everything as n goes to infinity. So, right, here's the picture for a real value function here on the graph. Here's minus n to n. There's my Qn, my rectangle Qn, and here's say height n, and here's f. Who knows what it does outside there, and so the black is f of x, and then let's make the red function capital Fn. I just, everywhere it's above n, I just cap it off there, and then I stop at n. Sorry, so those lines are supposed to overlap with each other everywhere else. So I don't change the function, but except if it's bigger than n or x is outside the ball of radius, the cube of radius n. Okay, so this is capital Fn of x, which is 0 everywhere else. Okay, and then now I'm just going to partition the range of capital Fn. So next, and this is going to be the big distinction with Lebesgue integration and Riemann integration, is that rather than partition the domain up, chop the domain up, we're going to partition the range of f up. So we partition the range as follows. So so for every fixed n and m bigger than or equal to 1, let's let E L M to be the set of x and Qn such that L over M is less than f n of x is less than L plus 1 over M. And this is done for every 0 less than or equal to L less than n times m. Right, because f is allowed to be height n, so I need to go up to n times m for L. So I'm just chopping this up chopping up the range into intervals of width 1 over m. Like that. And then set f and m of x to be equal to the sum over all L of L over M of the characteristic functions E, L, M, X. Right, so these sets, the point is that these sets here know about F, right? These sets know about F. It's all the X's and Qn for which F is between L over M and L plus 1 over M. So if I fix one of these bands here, let's see if something in it. I just now I get my set by looking at all the places where, so it looks like there's some stuff in here, stuff in here. So this is the set, one of these sets ELM, and then stuff in here, right? Stuff in here. So these purple guys are one of these sets ELM. So this doesn't look like how you partition things up usually in when Riemann integration. We're chopping up the range evenly, and then we get some funny looking set down below in the domain. And then now I just look at the characteristic function on these sets of I just make this equal to L over M, so the bottom of the set. So what my function looks like, yet another color, maybe green. So what my function looks like, no. Oh, I can undo it. What my function looks like is just this simple function here. And this green function approximates f on this purple set, right? Only on the purple set is this a good approximation. And then I just sum them all up, right? So sum them all up, and I note for every x, the difference between fn of x, which I know is already the fn is where I was just my truncation of my original function f. The fnm's are below it, right? This green function sits below the original function, the red function. No, the truncated function is a red function. X, and the biggest I miss by is 1 over m, right? Because right, I've just approximated here, but I'm only allowing the range of f to be between L over m and L plus 1 over m in this range here. So even if I just fix this equal to the bottom of the possible values that f could take here, I'm only off by 1 over m, capital M, for each of these guys. So I'm approximating from below. This is always a positive number, and I'm only off by 1 over m everywhere. Okay, right, because my capital I've summed up overall. So there are many such I did this in subintervals, and so I have a bunch of different simple functions here in this fn. This is a simple function, right? Okay, and now I'm basically done. So I just want to unify my indices. So now set n equals m equals 2 to the k. I want them both to go to infinity. For every k bigger than or equal to 1, a is n, and let's let phi k to be equal to f 2 to the k, 2 to the k. Then okay, for every x. And the phi k's are increasing. And satisfy all the properties. Right, why are they increasing? Well, if I chop up finer, all I do is possibly move up a little bit in some, uh, if I chop up this one set a little bit finer, then I just the green line only moves up, right? Does this make sense? This construction makes sense? So this is approximating measurable functions, non-negative measure functions from below using simple functions. In general, I can do almost as good. So the theorem is this: just if f is a measurable function, then maybe I should write this like this. Measurable function, no longer the requiring non-negative, then there exists a sequence of simple functions such that if I take absolute values of the simple functions, then they're increasing. And the limit as k goes to infinity of fk of phi k of x is equal to f of x. For every x, in particular, absolute value of phi k of x is less than or equal to absolute value of f of x. So in this sense, they still approximate from below. So when I moved rooms, I unplugged my computer, but I need my power cord. So just give me 1 second. So. So are there any questions about the previous theorem or any questions about the statement of this theorem? This is just a generalization of the one before, but now I allow for non-negative. Now I allow for a general measurable function. I can still approximate by simple functions, but in this sense, the sequence is no longer increasing, but the absolute value of the sequence is increasing. And the proof is just decompose f of x into f plus x minus f minus x, where f plus x is just the positive part of f. Equals the max of f of x in 0 for every x. And f minus x is equal to the maximum of minus f of x in 0. The note f plus and f minus are both non-negative. So I've written f as a sum of two non-negative arguments, and now I can approximate, right, I've written f as a sum of two non-negative functions, rather a difference of two non-negative functions, the positive part minus the negative part. And then I can just approximate that positive part by simple function, increasing sequence of simple functions as in the previous step, approximate the negative part by an increasing sequence of simple functions as in the previous theorem, and then just take the difference of those sequences of simple functions, and I now can approximate f. And apply, so the last part of the proof is apply previous argument to plus and f minus. Okay. And lastly today, the last theorem I want to state is that we can also approximate by step functions if we only ask for convergence almost everywhere. So remember, step functions are where the domains of the characteristic functions, or the supports of the characteristic functions, the sets over which the characteristic functions are defined, are rectangles only. So if f is a measurable function, then there exists a sequence psi k of step functions such that psi k of x tends to f of x for almost every x.
I have a question about the previous theorem.
Yeah, this one or the one before that?
The I guess the corollary.
Yeah.
Why does it follow from our construction that the absolute values are increasing?
Okay. So just the triangle inequality. So I think, yeah. So what can we do? So let's, so we have, let's call them phi plus k less than or equal to f plus, and phi minus k less than or equal to f minus, and then phi k equal phi k plus minus phi k minus. So I think this is the sequence of measurable functions we'd like to take to approximate the difference of f plus and f minus. And then so what do we know? We know that phi. Sorry, I should have just written this in terms of this is less than or equal to phi k plus 1 plus this is less than or equal to phi k plus 1 plus. Sorry, minus. And then, so phi k plus minus phi k minus. I'm rewriting things. I wrote that. This is less than or equal to phi k plus 1 plus. And then let's see. Oh, I should put minus 1 here. Oh, do I take the other ones to be decreasing? Decreasing, maybe? So I'm subtracting something bigger, so that's not good. Yeah, maybe I need to do something else. Maybe I need to absolute value. Sorry. Okay, sorry. I forgot about that. I forgot about what I was trying to prove. Sorry, Michael. So I I'd like to take. I'm taking the absolute value of these guys, right? But what is the absolute value of this? Well, this is a did I say this right?
Is it like that's the value is like one of those two, but like not both because like one of them is zero or something?
Yeah, exactly. Yeah. So um so um so yeah. I can yeah. So maybe I shouldn't write this. But that's the rest of the proof, right? So what can I take these to be? I can these phi k's are just equal to so all right. Let me erase what I was writing here and just explain it in words. But that was uh, just re-say what was just said in words. So what can I take these to be? Well, I can take remember when I constructed these guys in the previous step. Um, I didn't change uh, the places where there's zero. Where this if this function was zero in places, I wouldn't. That's equal to the value of the phi k's, right? So the phi k's aren't changed. They're just zero. They're going to be zero wherever f plus is zero, right? Each of the phi k's is actually going to be equal to zero wherever the f plus is zero. Um, so um, so where are we? So the absolute value is just going to be either uh, at any particular x, either phi k plus or phi k minus is going to be equal to zero, and then the absolute value is just going to be given by whichever one is not equal to zero. And then I have that. Does that make sense?
Yeah.
Sorry,
I was missing that part of it.
Yeah, that was I was too. As we started off. Okay. Thank you. Was that Faraz who spoke up? Thank you. Yeah, yeah. So it was slightly more involved than what I just said. You have to look back at the construction of how we would actually build these phi k's and phi k minuses, phi k pluses, phi k minuses, and note that only one of them is non-zero at each particular x. Something in the chat too. Thank you also, Joseph, for pointing the same thing out in the chat. Okay. Okay, so going back to where we were before, any other questions about the previous two theorems before I state the last thing from class? Okay, so this is extremely helpful. It's confusing. Just like measurability which sets are measurable is confusing kind of until you start breaking down what measurable sets really are, or how to roughly think about them. Same with measurable functions until we start saying, okay, well they're all just kind of obtained as limits of sequence of simple functions. So you can't quite say as much about step functions, but you can prove this weak result that you can approximate every measurable function by a sequence of step functions, as long as you only ask for the convergence to hold almost everywhere. And the proof, and let me just highlight this almost everywhere. The proof is just use the previous theorem. And our characterization of measurable sets. So previous theorem, we have a bunch of simple functions, which are weighted sums of characteristic functions. But then we know that every measurable set is you can find finitely many, every measurable set of finite measure, you can find finitely many almost disjoint cubes so that the symmetric, that approximate the measurable set in the sense that there's arbitrarily small symmetric difference. So use previous theorem and the fact that every measurable E finite can find finitely many almost disjoint cubes Qj such that the measure of E symmetric difference j equals 1, 2, and Qj is less than or equal to epsilon. For every epsilon, for every measurable set, for every epsilon bigger than 0, you can find such a collection of cubes. And now, so you can see here where almost everywhere arises, right? We're always missing by some epsilon, right? So the best we can do is almost everywhere. Okay, so I want to stop here because the next topic is going to be go along with with an in-class presentation on Thursday. So the next we're going to flesh this all out a bit more with the part of the book called Littlewood's Three Principles. So measurability and integration, as you might imagine, made some people uncomfortable at the turn of the 20th century. But I guess Littlewood was one of these people who could put others at ease and had three kind of helpful heuristics for thinking about functions, thinking about functions in this new world of Lebesgue integration. So we'll cover Littlewood's three rough principles for connecting the classical view of functions with the new world of measurable functions in Lebesgue integration next time. So you're welcome to read ahead in your book, and we'll start there next time. Are there any questions now in the last 5 minutes of class?
Actually, when we proved the powers of the measurable functions, do those apply to fractional or less than 1 powers, like square root of f? Like it's defined. So like if f was positive.
Yeah. So where are we here? Maybe it's. Did I miss? Yeah. So, so for example, down here, you could take G to be, so we could try and build from what we stated a little bit. Mm-hmm. So if I took G to be 1 over F, so maybe that doesn't make sense. So negative power 1 over okay, the proof I gave isn't quite enough, I guess, because I have to worry about so if I take 1 over, if I have a function, say just like a polynomial, right? If I take 1 over that polynomial, mm-hmm. Then I get a function that's not finite, right? I take it a rational function, for example. Those are measurable functions, right? Because they're continuous function except at the collection of their zeros, for example. Mm-hmm. So yes, this does extend, but you need to kind of keep track of the type of singularities that you allow.
I see.
So I'm not going to write something precise now, but for example, for rational functions are measurable functions. Mm-hmm. Um,
Okay.
Rational function and measurable functions. But and okay, so I have to think a bit about how to deal with kind of. So if you're taking complex analysis, there are these types of singularities. So there's singularities like those that rational functions have, and then there's things called essential singularities, like e to the minus z or something. E to the minus 1 over z or something, which is a bit worse. But as far as measurability goes, I have to think a bit. The rational power. If I have a set that say doesn't vanish, if I have a function where on a set which doesn't vanish, for example, and if I have I could take rational powers of this function. That's okay. The setting where you take so irrational powers of a function, that's you can phrase what does it mean to take irrational powers of a number? Well, you take some soup over rational powers where approximate the real number from below by rationals.
Yeah.
And those types of operations are fine when it comes to measurability, right? You can take unions of union over rationals of certain of sets. So that sounds okay.
Right.
For example,
Yeah.
does that make sense? So
Yeah, I think so. Yeah.
So like you could try and cook up things like in this example here, where we prove the measurability of f plus g by taking these unions of sets which we know to be measurable. So you can obtain that irrational powered function as some limit of rational powered functions, and that measurability is preserved under taking limits. So that should be okay. Yeah. Yeah. Any other questions? But I just wanted to emphasize that those like generalizations to what I stated have to require a little bit of thought. Maybe I should have emphasized, but. Okay. Okay.
What's the PSET schedule look like?
The PSET. So I'm gonna assign nothing due this week. As I mentioned last class. So I was giving a week off for PSETs, which means nothing due this week. And I'll assign a PSET on Thursday. It'll be due the following Friday. So I just wanted to catch up with lectures where we were in PSETs. We were rapidly diverging. I feared, at least, that the lecture were going a bit slower than what I had given already in PSETs. So,
can you synchronize the file?
Yeah, sorry. Yep. Sorry, I've been forgetting to do that more. That was good the first few days.
Thank you.
It should sync now.
Thank you very much.
Okay, guys. I'll see you on Thursday. Bye-bye.
Thank you.
Thank you.